All right, so without any further ado, please allow me now to introduce our first speaker, Dr. Nitish Srivastava. So Nitish is the CTO and co-founder of Vayu Robotics, where he works on physical intelligence for mobile robots with a focus on creating safe, scalable, and economically viable robotic solutions. Nitish is passionate about advancing real-world applications of autonomy. Before founding his company, Nitish worked at Apple on various robotics projects, gaining extensive experience in developing cutting-edge systems. Prior to that, he founded a company specializing in perception for autonomous vehicles, which was acquired by Apple. Nitish completed his PhD in 2016 at the University of Toronto, working with Geoffrey Hinton and Ruslan Salakhutdinov, who will be our third keynote speaker, where his research laid the groundwork for his career in robotics and machine learning. Please join me in welcoming Dr. Nitish Srivastava, who will be talking about simulation to train autonomous driving robots.
Thank you. So today, I'll be talking about what we are doing at Vayu Robotics and especially the role simulation plays in making all of this happen. So before we talk about that, just wanted to show you what we are building and what our first product is going to look like. So this is what the product looks like. We are building something that you could use to deliver groceries, food, things like that, from all the way from inside a grocery store. Like, for example, you can see here, somebody could pack your grocery order, put it in a robot, and the robot takes off. It goes through bike lanes. It pretends to be a pedestrian or a bicyclist, as it whatever works best, and then it ends up at a person's house. It can drop off a package and then go on its way. So this is what we are building. This is what the product's going to look like. And we are operating autonomously on public roads today. This is a picture from our 1,000th delivery that we recently completed, so it's a big milestone for us, some of our team members. So before we talk about how we build this, we should first talk about why should this technology exist? Why should we develop such kinds of robots? And there's two clear answers for this when we first started. First, it helps improve local commerce. So your local convenience store owner cannot hire delivery workers to do this. It's just too expensive to make that happen. So the cost of providing delivery today is already too high. Local restaurant owners, for example, struggle almost. If you pay $100 for your restaurant order, the restaurant gets only $60. Most of it goes to the deliveries and all the other things that happen along the way. So if you want to improve the local commerce in your city, it helps to have low-cost delivery happen. It also helps improve the bike lane infrastructure in that community, because there's more uses for that bike lane instead of just being for people on bicycles. The other important thing is that this type of technology helps improve the lives of delivery workers. So instead of one person doing one delivery at a time, one person can manage a fleet of 50 robots, effectively doing 50 deliveries at the same time. And then they can get paid a decent wage, and they don't have to go out physically doing this one thing at a time. I think human time is far more valuable than that, and a human skill is not utilized properly if they're just going to do this repetitive task all of this time. So that's why we want to build this technology. And why use bike lanes? So when we started this, we already had there were already sidewalk robots, and so these are bots that drive along sidewalks. But because they operate in that domain, they must be slow-moving. They cannot really move very fast, because then they would hit people and their pets and so on. And they also obstruct pedestrians, because sometimes sidewalks can be narrow, and they're really not designed for. They're designed for people. They're not really designed for this. The other type of robots that existed were larger delivery robots, and these drive in regular car lanes, but they must move fast like other cars, because they have to keep up with that type of traffic, which means that they have the similar regulatory as well as model barrier to deployment, because these things have to be really safe, because they have to move fast and they have to be just as safe as a robotaxi, for example. So what we decided to do was to build something that was in between, which is a bike lane robot. So a bike lane robot drives in bike lanes or on road margins. It basically drives everywhere where we would expect a person on a bicycle to drive on that road. And this gives us a good balance between speed and safety, because you can drive up to 20 miles an hour, and you can deliver large packages and grocery orders, but you have fundamentally only 1% of the kinetic energy of a car. So from a physics fundamental first principles perspective, you just don't have enough energy to cause damage in the world. You can have a short braking distance. Worst case, you can come to a stop. Like it's not as catastrophic as that happening in the middle of a road. So that's why we are building these types of robots. The other decision we had to make was what type of AI model would control this robot. And we decided that it would be a camera-based end-to-end model, something that takes camera images as input, along with other things like what route you want to drive at and what's your current speed and so on, and then output directly a path or a trajectory for the robot to follow. And we did this for two main reasons. There's an economic reason and there's a technical reason. The economic reason was that we really cannot afford to have expensive sensors on a robot that's doing deliveries. If you have a lot of LiDARs, if you have like heavy compute, you have a dependence on HD maps to localize accurately, that breaks the unit economics of the problem. You cannot make money at doing $2 per delivery and having a $100,000 piece of scientific equipment doing that. It's just not a business model. So we had to build something that works off of cameras, and cameras are cheap. You can get cameras for $50, like really good automotive cameras. So that was the business reason, and there was a technical reason as well, which is coming from my experience trying to build this type of technology for cars. The more human-designed modules you have in an autonomy stack, the harder it gets to propagate uncertainty through them properly, and the more brittle the whole system becomes. So, for example, if you're not able to detect a particular class of object, or you misclassify something as something else, that's very hard to recover from later on in the stack, and it becomes really hard to quantify uncertainty in the right way. Like, is this a person walking a bicycle, or is the person riding a bicycle? Like, these types of decisions have to be made early on in a perception stack, and then you have to live with that and the consequences of that later on. So, and like overall, what was happening in the AI field is that more and more we find that architectures that are more data-driven and less modular, less engineering-driven tend to work out. Like, for example, large language models, you just do next token prediction. You don't worry about how you do it. So with that same type of motivation, we decided we want to build a system that can just figure out what to do in the world and figure out the right representation to do it without us having to say, okay, you need to look for this type of entity and then this other type of entity. So that's why we are building this model. So how do you go about building and training something like this? So if you want to train a model that has an input X and an output Y, the easiest way to do that is to go collect examples of X and Y. So you could go collect real data in the world, but that's really challenging. It's really challenging if you wanted to, it's harder than when you want to do a self-driving car, because in a car you can sit inside it and drive, but a robot like this, you cannot just actually sit inside it. So what you can do is try to operate it remotely. So then you have to use something like this, this is our small remote operation center, where we try to, where we can, if we wanted to control robots remotely, we could drive them over the cellular network. But it's really unsafe if you want to drive at more than 5 miles per hour, because the reaction time, even if over a very good cell phone connection, is just not that good. The other thing what we've done is try to outfit a bicycle or a tricycle like this with our cameras, and then go and collect data to emulate how a human would drive in that same environment. But it's really hard to scale. You can collect some specific examples of this type of scenario, what you would do, but doing this for millions of scenarios and hundreds of thousands of miles is just not feasible. So we had to turn to simulation. So we used simulation to scale up the data that we train on. And at the time when we started, Carla was one of the great tools. It's an open source driving simulator. So we built a few different what we like to call bike towns in Carla. So these were towns which had some bike lane infrastructure, and then we could drive in those. So this is an example of a town we built. We built about 10 of these. And then we collected data. So the data looks something like this. You're driving around. You have to deal with, let's say, cars parked in your path. And then you just have to keep going around them and deal with other things that come in your way. So it could be other types of objects. The new types of obstacles could come up. You may have to deal with a lot of other types of pedestrian behaviors and so on. So like there could be like a random traffic cone in your path, or and then the bike lane may not be the rightmost lane. It could be a lane right next to a parking lane. So there's a lot of variations that could happen. And so we collected data that looked like this. And then we deployed this on a robot. So we took a lot of work. We did a lot of work to make the sim to real transfer happen. I'm going to talk about that later. But the end result of that was something like this. So this is our first robot prototype. This was about 2 years ago, running in a street behind our office. And it's driving here for the first time. It has no maps. It is looking at the street for the first. It has seen no real data at all, in fact. It's just driving. So it learned to do some things really well. It learns to stick to the bike lane. And it could do a lot of reasonably good behaviors that was really encouraging for us, but it was really not good at handling intersections and like doing more complicated things like that. So we decided that we really want to scale this up. So we want to go from the 10 towns that we could build in Carla to 100,000 towns. Like, how do we go build diverse environments where you could collect all sorts of data that would be needed to make this work? And so we built our own simulator. So what we like to call Vayu Sim. It is a fast, realistic, and scalable simulator. We built this in collaboration with our friends at Tempo Simulation, which is another startup who helps build simulations for people. And so then this is what our simulator looks like. We did a lot of work to make the rendering very realistic, also very fast, custom shaders to make the depth, image, and semantic segmentation happen in a single rendering pass. The simulator is fairly realistic. We could do lens artifacts, sun glare. It has really good quality pedestrians. We also did a lot of work on metallic, transparent surfaces, rendering things when you're very close to them, making them look very realistic. Importantly, we also had access to a lot of assets that are available in the Unreal Engine marketplace. So we're able to do something like have a whole bunch of bike lane users. And this was really important because we wanted to make sure our robot can function well with other bike lane users. And so we have a whole universe of them in our simulator. And these are extremely fast to render. You would see that it has a lot of diversity. You could have trailers attached to bicycles. You could vary things like colors and clothing and type of bicycle. You could also, as we'll see next, have people carrying goods. So you could have different types of attachments on them. And this is not really, I mean, and we hear a lot about like generative AI to generate all of these things, and those are excellent tools. But like you could just go on Unreal Engine Marketplace and download these, and just, these are available. So there's a huge amount of work that the gaming community has done to create assets, and you could just go and use all of them to train. And you can see these are not hyper realistic. Like you can clearly see they are not real, right? But this is good enough. Like our goal is to not like have pretty pictures. Like the goal is to not hit that person. So that's the level of realism we need to make this happen. And so in our simulation, we can do a lot of procedural random generation. So what that means is we can randomly create cities. So different types: high-rise, low-rise, suburban, urban. We can do parks. We can do trees. We can do a lot of these types of things. And it's all procedurally driven. So an artist doesn't have to go and create the city. It's all built randomly. So we can just like you can draw a random sample from a Gaussian, we can draw a random sample from the universe of road networks and then automatically build a city on it. We can do things like randomize a lot of things like sidewalk appearance. So we can have grass. We can have sidewalks at a level with the road. We could have dirt. We can look at something else. We can also randomize a lot of things around intersections. Like, for example, if you look at the road markings, there's markings where there's intersections where there's no marking. There could be zebra crossings. There could be just parallel lines and so on. Another important thing for us was getting the universe of bike lanes right. So there's a lot of different types of bike lanes. There's ones where there is a separate shoulder. Where there isn't a shoulder. There's buffer zones. There's different types of colors and dashes and hatchings and buffers, and there's a whole universe of things like that. And so we can now go and create all of these randomly and build this. The model now has the ability to understand like this general concept of a bike lane. It's not looking for anything specific. It just understands that the narrow thing that's next to the road is what it's looking to drive it. And of course, we can do lighting conditions really well. We can have the sun be in the view of the camera, and then it renders quite nicely. So, but then besides doing the visual rendering aspect of it, we could also do a lot of interesting behavioral things. So for example, negotiating with pedestrians is an important thing that we need to handle. So for example, here you see the view from the front of the camera, and this is the robot driving up to the intersection. It's waiting for the pedestrian to pass. And then after the pedestrian is passed, it moves up to the intersection. But now this pedestrian maybe wants to go back again, but they're waiting. And so the robot waits for them to see what they want to do, but then eventually has to go. It cannot wait forever. So it's developing these types of negotiating behaviors and doing that in a way that's natural and not impeding traffic was important for us. And then the robot keeps going, and then eventually it finds some trash cans down the road, like in this video, and then it has to deal with that. So it has to go around them. Another thing that we see a lot is cars parked in bike lanes. So, this is something that we have to deal with all the time. Is it has to the robot has to go out into the regular car lane, figure out when it is the right point to come back. Like for example, in this case, it reaches all the way to the intersection, and then it finds that now it needs to make a right turn, so it has to get into that lane and make a turn, but wait for the pedestrian to cross, and then it goes. And then while it's going, there's another car parked there, so now it has to go around that one again. So doing all of these things together, generating these scenarios randomly is something that our simulator is really good at. And of course, we are in the Bay Area, so we have to deal with roads in San Francisco that go up on a hill. And that's also especially challenging because you're going up and you really cannot see anything beyond that edge. It's blank until you go and observe that. So we are able to do that. We can go up hills in San Francisco and deal with things that happen there. And besides the more normal cases, we also can now generate a lot of rare events automatically in a more sort of ML-guided way. So we can generate uncommon interactions with road users. For example, a person on a scooter cutting in front of us. And we can generate variations of this. So for example, we can do very highly controlled scenario generation. So for example, this was the nominal sort of cut-in scenario, but then you could have the same person, different colored shirt, doing that at a higher speed. You could test the limits of perception and see if this thing is really going to work at low lighting conditions. You could have more pedestrian traffic on the sidewalk to see if this thing is still getting picked up. So the ability to do this highly controlled scenario generation is really important for driving and for generating this type of training data for training these models. And so using all of this, we are generating about 200 miles of really eventful traffic driving data per GPU per day. And this is far more than we could ever do with real data. And it's a lot more informative. There's interesting things happening, whereas in real data, mostly you're just driving down, nothing's really happening, and you just keep going down the bike lane. So this is what we found works really well. The way we learn with this data is also interesting. So we use what we call learning with an online teacher. So what that means is we have this concept of a student agent and a teacher agent. The student agent is this model that you're trying to train, and that gets as input sensor data. So it sees the cameras, and then it has to figure out what is the path that the robot should follow. The teacher agent, on the other hand, is a privileged simulation agent that has access to the details of what is happening in the simulation, so it knows exactly where all the different lanes are, where all the other actors are, what their speeds are, and their intentions are. And so it can use all of this information to come up with what we can consider a ground truth supervision. So it knows exactly what is the right thing to do in that environment. And this doesn't even need to be a neural net. This could be rule-based, could be search-based, and that could give us it a perfect ground truth. This is exactly what you want us to do. And so then we can use that to figure out how to drive. So for example, in this case, we have our robot, which is this, as indicated with this yellow circle, and then we have this other car, which is a taxi that we're really close to, and we may be about to hit. So what we can do is ask the teacher, well, what is the right thing to do in this situation? And the teacher can tell us, well, follow that yellow path. There's a no stop at the end, and that's the right thing to do. And so we can train the model to do that in this situation. But what we can do is we can go a step further. We can have an online teacher and an inquisitive student. What that means is we can have the student ask queries. So the student can say, OK, well, that was the right thing to do, but what about all these other things that I could have done? Why are they not the right thing to do? Or what happens if I do them? So the student can come up with these types of queries, and the teacher can try to answer them. And this is not something you could do with real data. In real data, you just see the path that you drove on. You have no way of saying why I didn't do that other thing, or what would have happened if I did. And that supervision is really important to train the representations in the model well. So, the simulation can give very detailed feedback. So for example, it can do things like assign a score based on different things that the model should attend to. So for example, it could provide a score based on distance from the bike lane center. So it could say everything in green here is more correct than everything that's in the red. So you need to prefer those over that. And because they are away from the lane, you could do things like sidewalk collision score. You could say the things on the red will lead you to a collision with the sidewalk, so you don't want to do those. You could also say, you could have a traffic collision score. You could say everything in red here is going to collide with other traffic, so you don't want to do that. So you can have very detailed supervision coming into the model. And that's really important because if you look at just the correct path, that is actually independent of that vehicle on the left. So if that vehicle wasn't there, you would still take that path. So if you were to just train on the correct trajectories, you're basically telling the model, ignore everything and follow the bike lane. That is what you're doing most of the time. And that would not lead to the right representation, right? So you want to be aware of that vehicle next to you. So if you were to just train on correct paths, you are really training on very rare events where that vehicle is actually important. So only when that vehicle cuts in would your path be affected. And how often is that going to happen in the real world? It's just very, very rare. So if you really want to train something that works and translates into the real world, you need this type of very dense supervision, and that is something that only simulation can provide. Another thing simulation can do is help you get into really hard situations. Because in the real world, when you're driving, you're typically trying to stay away from hard situations. You don't want to be in a situation where you're about to hit something or do something really bad. But what we can do in simulation is you can have a suboptimal student policy, something that was, like, for example, just trained on the correct behaviors. So it was just trained on the teacher trajectory and has no access to out-of-distribution states. So that type of student policy has a tendency to go off the rails. So for example, the magenta line here shows the path that the student would like to drive. And this is not an optimal student, hasn't really figured out how to drive correctly. And so it can sometimes go out of distribution. It can go really close to some other vehicle, for example. And in that case, the teacher can say, OK, the yellow path is the right one to do, so you need to do that. But the important thing is it got into that state where that supervision was elicited from the model. And getting into those states is not is very hard. Like, how do you know where to place the model in this environment so that something useful can be extracted from the teacher? And the advantage of doing this in a simulation is that you can use the suboptimal models, the models that you train along the way to your perfect model, to go and access those states. So you can go build that. So if you go and build that model, so if you train a student policy after adding data from states that were reached with the suboptimal policies, then the model can really go and avoid those types of mistakes. So this is that similar situation, and in this case, the model doesn't go off the rails. It can stay within the bike lane. And so all this is nice. Like, so at the end of this you create this flow where you're generating a lot of data by driving on what the teacher wants you to do. Use that to train a model. That model then drives the robot. It gets into these suboptimal states. You get more data from that. Then you retrain the model, and you go and keep improving the model that way. And so eventually you have a model that works really well in simulation. So it can really drive these cars. But what happens, but what does that mean for the real world? Like, how do you really transfer this into the real world? And that's the big question. How do you bridge the sim to real gap? So we don't want to just play a video game, right? We want to have a model that can that learns the right policy, learns the right representations, but it has to transfer to the real world. And so the simplest thing you could do is style transfer. So you could take all the simulation images and make them look more like the real data. So for example, you can make the skies look a little bit grayer, because that's what the camera usually sees, and things like that. But that really doesn't solve the full problem. This is not just a visual fidelity issue. It is really a generalization problem, because what you really want is that the model should, having seen, let's say, 20 different types of traffic cones, it needs to understand what that 21st type of traffic cone is like. Like, you really cannot have all types of things happen in simulation. So that generalization problem is the key thing. And how do we solve a generalization problem is we throw a lot of data at it. So we train the model on data from multiple sources. So not just the driving simulations that we've built, but also combine it with web scale images, text, and video, and real world data. So combining all of this in the right way really makes this model transfer well. And one way to describe this is like a training data pyramid. So if you look at it in terms of volume, the web scale images, text, and video is where you learn to see. So you could think of this like any other large multimodal model, like a GPT-4o, for example, these types of models. They have not done any moving around in simulation, but they have done things like seen all the images and all the text in the world. And that already gives them an idea of what the content of the world is about, what is a traffic cone, and what are people, and then maybe children are more likely to run your path than adults, and so on. So it has this common sense understanding from web scale images, text, and video. And then you apply that knowledge of learning to see to learn how to move. And that learning to move is what happens in simulation. So by factoring it into these two steps, your visual process is a lot more general, and it can understand how to contextualize things and how to, it gives it the ability to do a lot of zero-shot transfer. So if it hasn't seen a particular type of thing in the simulation context, but it has seen it in all its web scale data, it may already know what it is about, and it has a similar representation to something that it has seen in simulation. So, and then finally, the real world is more of a cherry on top. So you usually use it to align it to the real world. So if you think of it in terms of stages of training, we first train a powerful visual encoder. This is a model that understands images in general. It knows the names of things. And then we use that and train a sequence model that is working on robot perspective data. So this is where we are now looking at sequences. We are looking at data from the perspective of a robot. And now the model has to apply that general purpose understanding to explain 3D-ness of the world. It has to explain distances and paths and occupancies and occlusions and fuse information from multiple cameras. It has to understand that things move at various speeds. It has to understand the concept of a route that you want to drive on, and then so on. So that comes in at a second stage, but borrowing all that general purpose visual understanding that you get from web scale data. And then finally, we can do post-training on real data. And this is where we can train it on a little bit of data we collect from the real world to bake in preferences for how humans like to drive. This is the equivalent of a RLHF that you would do, or a GRPO that you would do on large language models. So there's a little bit of post-training to filter in, to add different types of qualities that you want the model to have. And to test that this is really happening, we took the representations that come out of the visual encoder and tried to train segmentation and depth models on this. And on the left, you will see those models running on simulated data, and on the right, you will see those same models, but running on real data without any fine-tuning. So on the left is a simulation image. We are running a segmentation model on top of the features that we extract from the visual encoder. And you can see the model is able to predict segmentation, it's able to predict depth. And those same models, having seen no real data at all during training, can already transfer. So we can get the same quality of depth representation. We can understand the segmentation properties. So all of this information is really baked into those visual tokens that you're getting from the model. And then how does that transfer in terms of the overall task? So you can see this is that same model that we saw trying to avoid cars in simulation. It is able to transfer that understanding to the real world. And this is, again, with no fine-tuning. This is without that third step of post-training. The model can already, without seeing any real-world simulated data, it can go and do this type of driving. So it can go around traffic cones. It can understand a person in its path. And we also tested it on more challenging situations, like having various road signs in the bike lane, going around structures like that. Again, dealing with obstacles in bike lanes is the most common hard situation that we have to deal with. So it can do those things pretty well. Open car doors was another thing we were happy to generalize to. Then dealing with a lot of parked vehicles and so on. So so that's basically how our model works. It can deal with some basic construction zone things as well. It knows not to go. So if it sees traffic cones, it tries not to go through them. It just waits for them to end. And so it's going, in this case, it runs to transition into a sidewalk from through an intersection, going around pedestrians. And the same model also works at nighttime. So same set of weights, but drastically different input. But because we train it on all of the data, it can also drive at nighttime. So so that's basically how our model works. This is transferred completely from sim to real with very little real data. So all of this is working today on public roads. So how do we make this happen? Our architecture looks something like this. It's simply combining transformers with state tokens. So we take images, we take the speed of the robot, we take the visual route, and so on. All of that goes into a model. We can actually work with any number of cameras. So because we add position encodings that come from knowing where the camera is placed and what ray was cast into the world to observe that patch. All of that gets added, and basically you get a bunch of tokens as in an input. And the key thing was, like, of course, we want to get temporal context into the model, but just having a lot of temporal context by just adding all of these frames makes the model very hard to run in real time on a robot, because it just has, if you have 10 frames per second, and then you have 6 cameras at reasonable resolutions, you just have hundreds of thousands of tokens that are coming into this model. You cannot just do full context. So history cannot just be context into a transformer. We had to condense it into a state. So after we made that happen, all of this really worked really well. So we got state into the model with the state coming in. The basic idea is the state gets updated looking at the new inputs, and then you get a new state. And then from that, we can query a lot of different things, like what's the spatial path, what's the temporal path, meaning where should I be at equal distances in space or equal distances in time, and what are my left and right link boundaries, and so on. So we can decode a lot of useful things from this representation. And we're able to run all of this on an edge computer that is in the robot. So in 46 milliseconds, we can encode all of this, and then 24 milliseconds to do straight aggregation. So in about 70 milliseconds or so, we can run this entire model, which gives us 100 milliseconds to run the rest of the controls and everything. So we have 10 hertz operation with this type of robot. So this model runs in real time, and not only does it perform well, but it also performs well in a way that you could understand, and it feels almost human-like. So for example, in this case, what we are doing is we are taking we're looking at the image that the model is seeing. The green dots are the path that it wants to drive at, but we're also looking at where is the model attending to. So we could trace the attention mask of these tokens through the transformer's computation and see if there's a spatial path that the model is predicting, which tokens did it pay attention to come up with that. And then we could visualize that, and you can see here that it's paying attention to that car, it's paying attention to the markers, the road markings. In this case, it's paying attention to, again, the road markings and that big construction vehicle on the left. And a new thing that we recently started working on is making the stop point that the model outputs a little bit more explicit. So we have that as an explicit output of the model. So the red dot that you see on the left is where the model wants to come to a stop. And we can trace back where in the image did the model look to figure out that stop point. And you can see that it has learned to pick the stop sign. It is also paying attention to the road markings corresponding to that stop sign. So effectively, the model has learned to detect stop signs and detect those lane markings without us ever asking the model to do those things. We're not saying, oh, go build like a lane detector, or go build a stop sign detector, or query this information from some map. It just figures it out that that's what it needs to do to drive well in this environment. There's another situation where it's trying to deal with this intersection. It sees a pedestrian crossing, so now it's applying those same weights to now become a pedestrian detector. So it's paying attention to those pedestrian pixels, and it's trying to see, okay, that's the reason why I'm coming to a stop here. So you have not just the good performance, but you also have explainability. You can see what the model is actually doing, and this is a very causal type of inference in the sense that it's not a parallel thing. It's not like you're outputting some language or something to just say what you're doing, but you're actually looking at the computation that derived that output. And that is telling you that this is what I paid attention to. So this works really well. Another amazing thing about this model is that it transfers to other robot form factors. So we take that same model that was trained with 6 cameras and from about a meter high camera, we applied it to a single camera about 30 centimeters from the ground. So this is running on a quadruped, and that same model is able to work. So it's able to deal with pedestrians, it's able to go around cars, and then so on. So the model is fairly general. It's not just about solving the bike lane driving problem for a wheeled robot, it can do other things as well. Right, so that's all I have. So the summary, in summary, simulation data brings unique benefits for training robots. It's not a poor replacement for real data. It's a much richer replacement for it. You can do a lot of interesting things in simulation that you cannot do in the real world. And the general purpose visual encoders really help sim-to-real transfer. So if you are training something in simulation, you want it to work in the real world, don't train your visual pathways in simulation. Train your visual pathways on the entire internet, and then apply those visual pathways to the simulation. And then, of course, at the end, we are capable of building autonomy modules that are performant, interpretable, and generalizable. So they're not, so this dream of building something that can take a lot of raw robotic data as input and output actions is quite real and practically happening right now. At least for wheeled robots, it's happening. So thank you. Happy to answer any questions. Yes?
Thank you very much. I think this is a very great, very insightful session. I just have one question. Have you tested on the extreme weathers of this block?
We have not tested on water because we don't want the robot to get wet right now. But overall, we have in simulation, we've done a lot of work on fog and rain and things like that. It is able to work on wet roads. So we have tested on wet roads, not in rain though, to be honest.
Gotcha. Thank you.
Yeah, go ahead. Sorry, there's a mic right behind you. Oh, here it is. There's a runner.
Oh, thank you. Thank you for your presentation. Is the goal to have these robots coexist with Uber and Lyft delivery people, or is it for Uber and Lyft to buy these robots to deliver for them?
So the question was, is the goal for these robots to coexist with the current delivery providers, or for those providers to use these robots? So I would say I think we are open on the business side. We could, we are operating. I think there'll be I think these robots are useful to those companies, and I think they would probably want to use them. So we are open to those types of business engagements. We could also approach this from a more, like your local grocery store could buy these robots and provide this as a delivery to their customers. So that's an alternative ownership model that could also work. So yeah, I think we are at this point exploring all options.
Can I ask a second question? Has anybody tried to steal one on the road?
So the question was, has anybody tried to steal one? So the answer is no. I don't think we've had that experience yet. But we are operating in like a nice suburb part of the Bay Area. So probably we haven't had those types of encounters yet. The robot is quite heavy. So you cannot like just steal it. I think you would hurt yourself if you tried to do that. But I think the vandalism is an issue. We've seen that with a lot of other autonomous delivery things. And I think society would have, I believe, at some point learn to accept these as, these are things that are going about doing a job and not for you to mess around with. So I think that will come eventually.
Okay, thank you.
Yeah.
A great presentation, thank you.
Thank you.
The robots are so cool. If I see one, I will steal. So could you comment on the hardware design limitations? I imagine you cannot put any hardware you want there.
Yes, so the hardware has to go through certain certifications for it to be considered roadworthy. So fortunately, the class of vehicles that our robot belongs to is more like an e-bike and less like a car. So it doesn't need a VIN number. It doesn't. So it goes through a different regulatory process. But it is similar to what an e-bike or like e-scooter would go through. So it's that type of framework. Yeah.
I think we have one online. We're going to move to an online question briefly.
Hello. Yes. The question is, with the end-to-end approach, how do you approach safety-related testing and verification?
Yes, that's a great question. So an end-to-end model gives you what you wanted to do, but it doesn't really, you have no way of knowing why. I mean, you can go and look at the attention maps and see like why it did certain things. But ultimately, like you want to prove safety, and you have to go and deploy this in the real world. So we have really two ways to do this. First is there's no this approach. An end-to-end model is no excuse for not doing a lot of real world testing. So ultimately, the statistics will speak for themselves. So you'll go and run this in a lot of situations, and we will prove that this model works and doesn't need interventions and so on. So that's going to be the real thing that determines safety. But in addition, like as we build this technology, it's not going to be perfect along the way. And so what we've done is built a complementary system that is what we like to call a guardrail. So you have the system that tells you, okay, this is the right thing to do, but then we have another system that's running on a separate computer that's doing very simple, low-level, almost physics-based checking of this path. So it's saying, is this path going to collide with something? Or is this path feasible? Like, is this something the robot can execute? Is it going outside the lanes and so on? So there's basic checks like that we intend to have on top of this. And the idea is that verifying a model's safety is probably easier than coming up with a safe solution. So it's like the P versus NP type of problem. So we feel that a simpler model can provide a safety envelope within which a more intelligent model can be deployed. And that's really how we want to go about proving the safety of this model.
Let's hear from in the room.
So great presentation. I can't wait to use one of these. So given that you have so little real world data, can you expand on how you prevent overfitting to the assumptions baked into the simulation? For example, like if you had never seen a pothole in the bike lane, how do you extrapolate to that?
Yeah, so I think that's a good question. I think if you've not seen something completely in simulation ever, you may have a hard time generalizing to it. You would have seen some of it on the web, so you would have some representation of like maybe a pothole is similar to some other type of thing that you may have seen in simulation. But if it's a completely separate thing that you've just never had experience on in simulation, yeah, we would just have to add that to the simulation. There's no magic here, like it's not going to just work there. And really the way we want to make this happen is quick feedback. So we go and test, we find something that we don't have in simulation, go feed that back, and quickly be able to create that experience in simulation. So it's about closing that loop as fast as possible and seeing more. And of course, real world data is still there. That is, as we go and scale, we'll have a lot more real data, and then we can go adding to that. That adds to the amount of training we can do, and amount of training that we have.
Thanks.
Thank you.
Thank you for the presentation. I find it fascinating, robotics. What were some of the barriers that you encountered to deploy this thing on bike lanes? And have you thought of other use cases besides delivery?
Okay, so the question was, what are the barriers we faced for deploying this in a bike lane, and what other use cases it could have? So I think the main barriers were, like we wanted to get approvals from the city, and the city wanted to be respectful of the biking community and so on. So I think that getting through those approvals and bringing everybody on board took some time. Overall, I think the city was welcoming. The biking community is actually helpful because they also want to have more bike lanes. So having more uses for this type of infrastructure is something that everybody wants to see. But getting all of that, putting all of that together was one hurdle. And the other thing was really just I think operating these robots, taking them from office to bike lane, like all of that, just dealing with hardware is hard. Like just transporting them in a truck to some place, like those types of things it just slows things down. It's not as quick as you check out some code and work on it and put it back. So I think those were one of the hard things we had to encounter. In terms of applications and other use cases, yes, I think the technology is fairly general. Like as we see, we were able to apply this on a dog robot. So we think it could do this type of thing could also do not just last mile, but last feet. It could take you right up to the door. So I think we can do a lot of other types of use cases. We can also operate in other operational domains. There's really nothing specific about the bike lane on the training side. I think if you can generate a simulation environment for another domain, we could go use this. So we are building this out in a very general way. We ultimately want to be the force that drives all robots. So we can go do that. Like the idea is to build something general purpose. That's why it's built off of web scale data. It's built out of end-to-end model. There's nothing specific about any particular domain. Thank you.
Let's take one more in the room.
Hi. So I was just wondering, like, how expensive are those robots? And given the current landscape of the competition in the robotic industry, like, how hard is it for you to generate interest from potential investors?
So it's, I think, so the question was how expensive are the robots and how how we are doing with the investments and into the company. So I think the answer to that is the robots. So we are trying to build the robot in a way that in mass production it costs it's around $5,000. So that's what we aim this number to be. We don't want this to be $100,000 robot. So I think that's, and we have kept that in mind. I think in terms of investment, I think the robotics is seeing a resurgence in interest. I think there's a belief that the type of generalization we've seen in general AGI is going to transfer and going to be impactful in robotics. So we are seeing a lot of interest from that perspective. I think there's a strong belief that physical computation or physical AI is the next big thing that's going to happen. So it's a great time to be working in this field. Yeah.
Let's take final question online.
All right, the question is there real-time communication with the robot? And what would happen in an unexpected situation where the robot freezes? Can the team take over control over the robot?
Yeah, so we do communicate with the robot. We have the modems on the robot that can use the cellular bonding technology, which is basically we have multiple SIM cards on the robot that can go talk to multiple cellular networks. And depending on load shift, any command that you give, the packets get sent to multiple people, multiple cellular providers get stitched back. So it's a really efficient network. We can do sub 100 millisecond control for the robot. So it's fairly efficient. We can go talk to the robot. If it completely shuts down and that should not happen, the robot is not designed to be that way. I think there's some component of the robot that is going to be active and we can go and control it remotely. But as we do a lot of this testing, we do have local operators present who can come and help the robot if it needs any help.
All right. Thank you very much.
Thank you.
Let's congratulate and thank Nitish one more time.